but you know, this student still got a problem. Okay, and to be honest, because I'm not beside your, you know, computer. I don't know what kind of procedure you're doing. Even if you post the screenshot, you did not post this procedure that you did. Okay, you see what I mean? So it's not gonna be easy to figure out what exactly your problem is gonna be. Okay, I honestly tell you that. I think that the most important is we have to try, you know, several times to figure out what is the problem. I mean, seems like those you know, instructions, it's like you tested it many times and you got the experience and say, oh hey, you know, like any other software, right? So if you guys don't want it, I mean, I personally think that if the virtual lab works, it will help you better because it's pretty much imitate the physical lab. But if you don't want and you want to switch back to the MATLAB, and then that's really, you know, just you know, very very what do you mean, Fatima? There is a submission, you know, site. You need to submit to the report. What do you mean? Where can you post? I don't understand your question. When you finish it, why you talk about you know, post? You mean submission, right? Oh, it's probably I have not made it, you know, available to you because the due date is not yet. So yeah. And seems like I have to extend the deadline for the lab 1. Okay. Don't worry about the submission. Okay, the submission will be there. That's not an issue. Okay. No, we're gonna extend that. Okay. Okay. But the most important is that should we continue or not? It seems like a majority of you don't agree to continue with the virtual lab. Is that right? Okay. Continue. Well, the first lab, you know, you still use the virtual lab for the first lab. No, there's no change to the. You should not switch it to the, you know, the MATLAB. You should finish it. I will extend the deadline to give you more time to finish it. Okay. Okay. So if we decide to switch back to the MATLAB, it's gonna start from the lab 2. To be fair to everybody. You see what I mean? Okay. Okay. So yeah. So I think that we cannot continue. You know, we cannot, you know, spend more time on the discussion this. Okay. So okay. Now the decision. I will post an announcement on the lab on the Blackboard. Okay. That might be a good suggestion. So do you want me to give you the option? I think that's a good suggestion. Okay. Yeah. Okay, but it will not be give any credit, you know, for when you choose any one option. Will you agree with that? That should be on your own decision. Tara, don't cry. Okay, you know what? It's always good to it is always good to. Okay, how about like this? Okay, I will give you the option. Okay, either use the virtual lab. Seems like you still like the virtual lab. It's just it does not, you know, work smoothly. Okay, which We can understand. We have 90 students. I already talked about it. I already asked, the technician how many licenses we should have. And actually, our technician told me that it's infinity. It's infinity. Okay, it's unlimited. Okay, so, but I guess that if everybody, because you see this virtual lab, it's actually installed in Quanza's server, not on our university server. The university is a portal. It's only a portal. Okay. Okay. So anytime when you guys work, you're actually logging into, Quanza's server to work on those virtual lab. You see what I mean? So I think that might cause some problem when everybody, when more users, get into it, right? And also, also, you never know how many users, from University of Windsor, it's our class use it. We don't know if at the same time, if other university has used it or not. We don't know, okay? We don't know that. Apparently, Quanza did not, okay? So, I think that, yeah. Well, Adam, there's not a fair or not fair. It's your option, okay? If you work on the virtual lab, no bonus, definitely no bonus. Okay, it's on your decision to. I give you the chance to have a better experience with the virtual lab. Okay, and you can try it. Okay, but if you cannot make it, and then you come back to at least you have the bottom line. You see what I mean? Okay. Okay, yeah, Brian, that's well said. Okay, all right, okay, so let's stop the discussion, okay? Stop the discussion, okay? Brian, I agree with you. I agree with Brian too, okay? Okay, let's stop the discussion, okay? And the decision is gonna be like this, okay? And starting from the first, for the lab 1, to be fair, everybody has to finish it, with the virtual lab, okay? And I will give you the extension of the deadline, okay? And the second, I will, starting from the lab 2, I will give you the option, and you can either use the virtual lab or use the MATLAB, okay? And you will get equal credit. You see what I mean? Okay? Okay. Yeah. Okay. Stop. Okay. Now that's it. Period. Okay. Okay. And also for the assignment 1, because I think that probably a lot of students stuck with the lab 1 for quite a while. Okay. So I will also give you the extension for the assignment 2. Okay. Okay. The extension of the deadline for the assignment 2. Okay. Okay, yeah. Okay, now stop discussion. Okay, now we need to have the lecture. Okay. Okay. So yeah, we're gonna have. So in the last class, I talked about the relation between the open loop system and the closed loop system performance relation, right? Because that's what we needed, like what I said. That is exactly what we needed. What we needed for the control design. Because we want to work on the open loop system, not on the closed loop system, right? I repeatedly emphasize, you really need to get this point, okay? Because when you work on the open loop systems information, it will have a lot of advantages, okay? And any design, if it needs the closed loop, system model, that's not information. That is not a good design method, because you see, before you figure out, you see, this is the conflicting issues, right? You see, like in this picture, here I said that this G of S actually is including both the plant and the controller. How come you have not figured out the controller design? How come you know the G of S? If you don't know the G of S, how do you know the closed loop? You see what I mean? So if you need a closed loop information, then you got to stack it. Okay, which one first? You have the controller first. You have the closed loop, system information first, right? We can only be given the closed loop system performance design, the requirement, right? That one, it's okay. Say you want a closed loop system stability, you want a closed loop, tracking performance, you want a closed loop the transient performance. That are the performance index, performance, criterion that we needed. That is okay because that's our goal. Okay, but the design method should not require the knowledge of the closed loop systems information, the model information. You see what I mean? If you stuck, with the closed loop system model, just like the Rose-Hurwitz criterion, right? You see, let's say I keep mentioning that the Rose-Hurwitz criterion is not like the Nyquist stability criterion. It does need a closed loop system model to allow you to apply it to get the information of the closed loop system stability, right? If you do not have the closed loop system's denominator polynomial, then you cannot apply the Rose-Hurwitz criterion, okay? But before you figure out the control design, you don't have that information. So basically, the Rose-Hurwitz criterion, it's not a good, tool for design. It is a good tool for analysis, but it's not a good tool for design. You see what I mean? Okay, so yeah, we spend a lot of time to talk about the relation between the stability and the between the open loop information and the closed loop system stability, right? Which is answered by the relation is answered by the Nyquist stability criteria, right? And also I talk about the tracking performance, right? The tracking performance, which is it's here, okay? It's here, right? So we know that as long as we reconfigure the open loop system model into this kind of NK type, okay? Well, I don't need to say more, okay? I've already said this too many times. You should know that, right? How to reconfigure the model of GFS, into this kind of format, and then you will be able to tell the closed loop system the tracking performance, right? And for the transient, I said that the situation is a little bit more complicated because the performance index defined is multiple. So, and also the performance requirement for the first order and second order system, they are different. So normally for the first order system, it's simpler. We only need one parameter to characterize, okay, which is a time constant, okay? But for the second order system, the situation is not that easy. Okay, then in order to demonstrate the relation, we use a standard second order system as an example to show you what kind of a relation, okay? And actually, specifically, we decompose the the standard second order system into an open loop system plus a unity feedback structure, okay? Solely because I want to show what is the relation between the open loop system and the closed loop system transient performance. And for that, we find out that the phase margin of the open loop system, right? The phase margin is read from the open loop system transfer function, right? So we find out that, oh yeah, the phase margin is a very good, performance criteria index, okay? And this can be read from the open loop transfer function. While at the same time, we find out that the relation between the open loop system's phase margin and the closed loop system's damping ratio, okay? The relation is actually for a certain kind of a range, the relation is straightforward and simple. And that is something we like it, okay? Because you see, right now, you can see that if you read the open loop system with a phase margin, you can predict what is going to be the closed loop system's damping ratio right away, which is very nice. And also, I said that this phase margin actually is the extension, it's a generalization of the damping ratio, okay? We use the second order system to show this relation. And for the second order system case, the phase margin does have a clear and explicit interpretation of the damping ratio. However, because for the high order system, okay, we don't have the, the clear and explicit definition of the damping ratio, right? If we have any system that is above the third order, we actually do not have a very clear, definition. So what exactly is the damping ratio? Okay, but in this case, because we know that the phase margin actually indicates the damping nature, so that's why for the phase margin has another, has another application. It's that for the high order system, I actually forget about the damping. I can use actually straightforward the open loop system phase margin to indicate the damping nature, even if I don't have a clear definition and a clear interpretation. Okay, so from now on, you should treat that the phase margin represents the damping nature of the system, regardless of the order of the system. You see what I mean? So this is a generalization of the damping concept. Okay, so you can see this phase margin is a very good quantity that we figured out. Okay, so that is why the likelihood stability is very, very popular. Okay, in the control design, in a lot of system, any engineering that needs the related to the system. Okay, so the likelihood criterion found a lot of applications in this case. Okay, because the phase margin is really very excellent concept. Okay, now on the other hand, we also developed the phase margins crossover frequency. Okay. See, the phase margin is really important. Actually, both quantity. Okay, the phase margin crossover frequency and the phase margin itself, both of them are useful. Okay, because the phase margin crossover frequency actually has a relation to the closed loop system's bandwidth. Okay, omega b. Okay, it's an indication of that bandwidth, and that bandwidth is very important. It's another important performance requirement for the closed loop system, for our physical system, right? So that's why we can summarize it the relation in this two quantities case. You see, crossover phase margin crossover frequency and the phase margin itself, and their relation to the closed loop system damping and the bandwidth. And by the way, when we have the bandwidth, we use the bandwidth, we don't need to use the natural frequency anymore. Because you know why? Because the natural frequency and the bandwidth, they're exactly the same. Okay, they're exactly the same. They are indicated in this relation. Okay, in this equation, right? Okay, you see, they're pretty much can be used alternatively. Okay, so that is why we normally only use bandwidth as a performance index, because if you know the requirement for the bandwidth, you know the requirement for the natural frequency. Okay, and then you know what you needed for the phase margin crossover frequency. Okay, and this is how the this what I just said, how we read it from the Bode plot. I don't need to mention this because I already talked about that when I talk about the Bode and the Nyquist plot, right? So like what I said, the Nyquist plot has a good interpretation of what happens. Okay, the phase margin, gain margin, you can see it clearly. okay? And geometrically, it is good, okay? But the problem is that the Nyquist plot is not good for the design, to play with the design issues. It is the Bode plot that is easier to be played for the control design purpose. But unfortunately, the Bode plot, they have only the mass, interpretation of the gain margin, and you see, crossover frequency, gain margin, phase margin, this kind of issues. Not as straightforward as the Nyquist stability, Nyquist plot. Okay, so you should be familiar with both plot. Okay, you should be very good to switch between the plot. Okay, so if anytime when you are not quite sure what happens, go back to check the Nyquist plot. Okay, so if you know what you want to do, come back to the Bode plot to do the design, to do the calculation, because this is going to be much easier in the Bode plot. So that is how you apply, how you can use these two plots appropriately. Okay? 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 So you need to know both plots. That's the bottom line. Okay? Okay. So now, should we say the design of the control design, you know what? From this relation, I actually can reduce the control design, to a very simple words. Okay. So what do you mean by the control design? Okay. Once you know your closed loop system performance requirement, you know what? Sometimes I can even bypass the closed loop, system performance requirement. I'm not going to say what I want for the closed loop system. I straightforward saying that what I want for my open loop system. Okay, that's the same thing, right? Okay, for example, I'm going to say, okay, I want a control design such that the system, the open loop system, has this much phase margin at this much specified crossover frequency. Okay, so the control design actually can be reduced to that if you can find a controller to achieve open loop system's phase margin at a specified crossover frequency. You see what I mean? Okay, you see the control design problem becomes the goal of the control design becomes this. Okay, as long as you can do this, then you achieve the corresponding closed loop performance requirement. No problem, right? Okay, so now next, what I'm going to show you is the two design, is the phase lead and the phase lag compensator design. And we're going to see how we can manipulate the control, extra control, and such that the open loop system will achieve a desired phase margin at specified crossover frequency. You see what I mean? Okay. Okay. Now, yeah. Before I go for the to present the phase lead, phase lag, design, I want you to pay attention to this figure. Okay, because this figure it's a further details and that how you can get from the Bode plot for the tracking performance. How you can read from the Bode plot for the tracking performance. Okay, for example, if you have a type 0 system, and basically you can read the KP. Okay, in this case you have the KP, right? The position error constant. You can actually read the KP from the low frequency, magnitude. Okay, because you see, if you have type 0 system, n equal to 0. Okay, this is a type 0, n equal to 0 case, and if you can test it, your low frequency will be always flat. Okay, you will always start, the magnitude will always start from a flat magnitude. Okay, like this. You definitely will see this kind of flat line in the low frequency, very low frequency. Okay, starting. Okay, that magnitude actually can give you the information of the position error constant. Okay, How to read it? It's specified here. You see, it's specified here. Okay. Now, if you have a type 1 system, which means that n equal to 1, okay, you have one integrator. If you do, approximation of the Bode plot, you're going to find out that, you see, the approximation is down here, right? You see, in the low frequency range, actually, the magnitude is equal to this, k over j omega n, okay? This is the base that how you can read this tracking performance error constants from the Bode plot, okay? You see, n equal to 0, you have the flat because you have only gain k. N equal to 1, you have one integrator. So in the low frequency range, you definitely see a magnitude that is a downward line with a slope that is what? Negative 20 dB per decade. For sure. Definitely is like that. Because you see this one, and when n equal to 1, you have a j omega in the denominator. So in the low frequency range, it will definitely for sure showing a downward line with slope that is minus 20 dB per decade. So in this case, you extend that the low frequency magnitude, find out the crossover point with the 0 dB, then you can actually find out what is the velocity error constant from that, okay, from this reading, okay. See, this frequency actually just right equal to the error constant, velocity error constant, okay. That will be straightforward, okay. Now, when you have a type 2 system, and you're gonna see in the low frequency range, you're gonna see a downward line, but with a slope that is minus 40 dB per decade, right? Okay, so you see on n equal to 2, you have a j omega's square. So definitely you're gonna have this downward line with minus 40 dB per decade. So in this case, once again, you just need to find out the extension of this magnitude with the crossover, point with the 0 dB, and this corresponding frequency is going to be equal to the square root of the Ka, the acceleration error constant, right? Okay, so this is the way that you can read from the Bode plot. Okay, you cannot read it from the the Nyquist plot. Okay, so this is, you see that this is a better way to use a Bode plot instead of a Nyquist plot. Okay, so that is something that you need to pay attention. Okay, you need to know. Well, if you do not go for this way, you can still find the Ka, Kp, and the Kv, right? You can still find out that. Okay, but it's just if you know how to read it from plot, you have one more approach to get this information. Okay, so it will give you the flexibility. Okay, sometimes it's easier to read it from the plot. Okay, so yeah, so we're gonna see what exactly it's gonna be the the control design. Okay, so before we go for the control design, you know what? I'm gonna show you that. Okay, this G of S actually it's a combination of the P and the C, right? Okay, and I've talked about this many times. What does this mean is that this is your plant model, which is your systems model, and this is the controller to be designed. Controller to be designed. Okay, and initially, you first step, it's always to evaluate the P of S when assume that the C of S is equal to 1. In other words, without the control, you're going to evaluate the open loop. You see, without the control action, your plan model is the open loop system transfer function, right? So you evaluate, when we say you evaluate open loop system, that's just like that you evaluate the plan model itself. That makes sense because you need to identify what's going on with your system, right? Okay, if it is good, if it is bad, and if it is bad, what is bad? That's something you need to identify before you can go for the control design. If you don't know what is the deficiency of your plan, how can you, what is the base for you to go for control design, right? Okay, so exactly the control design is that, okay, if this guy does not satisfy my closed loop, requirement, okay? You see here, I'm using the relation between the open loop system and the closed loop performance, right? Okay, so when we evaluate that, we already know, we're gonna know what's the deficiency between the open loops using the plant itself to form a closed loop and the desired closed loop system, right? Okay, you're gonna identify the deficiency, okay? Okay, and then if PS cannot achieve the satisfy the closed loop performance, then what? Like what I said, because this is the plant, that normally you can't change the design of the plant. Okay, you're not the designer of the plant, right? You're just the user of the plant. Okay, but it just you find out that this guy does not work well. Okay, so what are we gonna do? If it does not satisfy your expectation, okay, the only thing you can do is to add extra CFS, the controller. Okay, this CFS is in your hand. But what is going to be the base for you to figure out this CFS, the controller? Yeah, you see, we do have the base. It's that we're going to find out the C such that this control the open loop system, right? Control the open loop system, GFS. Okay, such that this GFS, it's going to show what I want. Okay, then that raises one question. So what is going to be the ideal shape of this open loop controlled open loop GFS? Idea. I'm talking about idea because I just want to know that not all the time you can achieve that. Okay, otherwise we won't call it idea. Okay, right? We just call it best. But unfortunately, this is just an idea system. This is just the wish list. Okay, but in practice, we are not always can achieve this kind of idea, performance. Okay, so but still help you what constitute a good system. Okay, so it is all characterized in this figure. Okay, see, this is the Bode magnitude plot. Okay, let's see what an ideal open loop system will yield. Okay, you see, if you look at that, this is the low frequency range. This is the phase margin crossover frequency. Okay, phase margin crossover frequency. Okay, this is the high frequency. So this is the low frequency range. This is the phase margin crossover range. And here is the high frequency range. Okay, so roughly any system can be roughly classified into this 3 frequency range. Okay, so in the low frequency range, what do we need? We need the magnitude to be high. Why? Because you see the track. This is because of the tracking our requirement, right? Remember, you see the tracking. You see KP. If you find out the position error constant, then you know that the tracking with respect to unit step signal is equal to the error is equal to 1 over 1 plus KP, right? From that chart. Okay? From this chart, right? See, we can find out that the tracking error will be equal to 1 over 1 plus KP. In other words, the KP, the higher the KP, the smaller the error. So same thing for the the KV and the KA, velocity error and the, acceleration error, right? Okay, so you can see that that will make the ideal systems that, okay, what do you exactly want in the low frequency range? Well, you want a higher KP, KA, KV. That means that you need to make the low frequency range magnitude as high as possible, right? It makes sense, right? Okay. And so now you can understand why we need more integrator, okay? Because you know what? If you have one integrator, minus 20 dB per decade, the slope. If you have a two integrator, it will go to the, minus 40 dB per decade, right? Okay, which one has a higher magnitude? Apparently, if you have a double integrator, your magnitude could go, much higher, right? So now you can understand why you have two integrator. It will have better, tracking performance than the one integrator and the no integrator case, right? The type 0 and type 1. The higher the type, the better the tracking performance, right? Because you can track more signal, okay? Either perfectly, or if it is not perfect, you can reduce the error, okay? So there is no doubt about that. Okay, for the low frequency, we want this, magnitude to be as high as possible. Okay, now then let's move to the, the crossover frequency, range. Okay, now you see, unfortunately, if you have a steep, crossover here, you're gonna find out the system will not be stable. Okay, why? Because you see, we said that the slope here actually represents the order of the system showing up in this range. Okay, see, if you have any crossover that is more than 40 dB per decade, okay, to the crossover, okay, any crossover line around the, this omega C range, okay, this is actually we use the omega PM, right? Okay, the phase margin, crossover frequency. If you cross that with a slope that is more than minus 40 dB, you know what? You forget about it. Your system will not be stable. Okay, so if you figure out what does this mean is that if you figure out the controller and then evaluate the G of S, and you find out that here your crossover it's more than steeper than the minus 40 dB per decade, forget about it. Your crossover system will not be stable. Okay, your crossover system definitely will not be stable. So what you need here is a flat crossover. Okay, less than minus 40 dB. Because you know why? Because if the crossover is more than minus 40 dB, your system is gonna yield the phase, negative phase is more than minus 180 degree. You can draw the Nyquist plot for that case. The system, the encirclement around the system, around the minus 0 point in that case will happen. So the crossover system will not be stable. You see what I mean? That's the reason. Okay, because in this case, you're gonna have a negative phase margin. Okay, you're gonna have a negative phase margin. Okay, you have too much negative phase. Okay, you have too much negative phase. Okay, but if the crossover, slope it's less than minus 40 dB, then you know that your phase lag, the maximum is no more than minus 180 degree. Okay, which you could have reasonable phase margin. So that is why there is a good chance for the system to be stable. Okay, there's a good chance, okay, for the system to be stable. Okay, so this is one indication. So this is what we needed. Okay, what do we need? Okay, and now for the high frequency range, you see, let's say this is your bandwidth. The bandwidth indication. Okay, because you're using omega m to indicate where the closed loop bandwidth is, right? So what does this mean is that in the high frequency range, which is above the bandwidth, you know what? You need the magnitude of the, the open loop system to be what? To be roll off faster, as fast as you can. You can understand, because you see, if you have the magnitude roll off, faster, steeper, drop faster, this means that any frequency signal above this value, above this cutoff frequency, will be hard to pass through the system. Now, what exactly in this range? What exactly is going to be the nature of the signals in this range? Noise. Okay, so for noise rejection purpose, we want the high frequency range magnitude to be, as low as possible. Okay, to be as low as possible. Okay, so it will, attenuate the high frequency noise, big time, right? So exactly this. Let me erase that to show you this desired, open loop systems Bode plot. Again, I'm saying that this is the desired. Okay, I'm not saying that you can definitely achieve it. Okay, you know why? Because you see, you need a magnitude here is steeper because you want a higher magnitude, right? At the low frequency range. How can you guarantee that it becomes flat across the phase margin crossover frequency? Okay, these two requirements, they are inherently conflicting. Okay, they are inherently conflicting. You got to be careful to play with that. Okay, it's not gonna be like you see, if you say, oh yeah, I can raise the magnitude at any place that I want, and also I can make it flat at the place that I wanted it to be flat. You know what? That's like a free lunch. Okay, that's like a free lunch. It's not easy to make it happen. Okay, in practice, normally it is hard. Okay, so that is why you need, actually sometimes you need to do the trade-off. Okay, you need to do the trade-off. You need to sacrifice the tracking performance a little bit and to accommodate to the crossover requirement, because a crossover requirement is definitely more critical, right? Okay, see, if you don't have the desired crossover frequency slope, your system becomes unstable. Okay, if the system is unstable, you see, let's say if you have a crossover here, the closed loop system becomes unstable. Do you still want to tell me that how high the low frequency magnitude is going to be? It doesn't make any sense, right? Because the closed loop system becomes unstable. Your high magnitude in low frequency does not make any sense. Okay. So that is why in practice we need to do trade-off here. Okay, it's not always that you can achieve this ideal Bode plot shape for the open loop system. Okay. So now we can talk about the design of the lead lag compensators. Okay. Now the design, it is like what I said. The purpose, if we use one sentence statement to describe what exactly is the lead lag compensator design, and this is it. Okay, this is just when we say lead lag design, we mean that we use the lead lag factor C of S to manipulate the stability margin and the 0 dB crossover frequency, which is the phase margin. Phase margin, this is exactly the omega PL. Okay, 0 dB crossover frequency, that is equivalent to say that the phase margin crossover frequency. Okay, so they're the same, right? Based on this figure we talked about before, right? Okay, so now, then first question is that what constitute the phase lead and the phase lag compensator? Well, this comes from the definition that we talked about before, right? So when you have a transfer function, we define the phase lag and lead and lag transfer function. If you remember that, we use the transfer function's phase If it is a positive, if it is a negative, to define it is a lead factor or lag factor, right? See, specifically, if this transfer function of the controller yields a positive phase, we call it a phase lead compensator. And if you have a negative phase, we call it a phase lag compensator. And don't forget it, on the Nyquist plot, we have a very clear indication of what a phase lead and a phase lag compensator means for the Nyquist plot, right? You see, let's say if this is the Nyquist plot of G of S, of this one, of this guy, okay? And then you add a phase lead compensator. Can you tell me? Just tell me in terms of the phase purpose, where this plot is gonna go. Use simple words to tell me. Someone, can you perceive that? You see, if let's say if this plot is the plot of G of S, now you apply a C of S that is the phase lead compensator with a positive phase. Can you tell me how you're going to predict this plot is going to go? Because we are talking about the CS G of S plot, right? After you apply the C of S, the controller, then you plot, actually we're talking about this guy's plot, okay? That's still open loop, right? Okay, can someone tell me, can you predict where the plot is going to go, roughly, in terms of phase? Someone? Come on. Come on. Quickly. Someone. You know what? If you don't volunteer, don't do voluntarily, I will name it, okay? I will call the name, okay? Yeah, okay. Yeah, that is good, Samantha. Yeah, and no budget, okay? Yeah, it simply to say you're gonna predict that the plot is gonna rotate counterclockwise, right? Because you add a positive phase. At a positive phase, this is a negative phase, remember? This means the phase is negative, right? So you add a positive phase, then you're going to drag this plot, counterclockwise. Okay, when you drag counterclockwise the plot, what happens to the alpha? Phase margin becomes larger, right? See, from the Nyquist plot, it is straightforward to see that if you add a phase lead, then you're going to understand that when you apply the phase lag compensator, because the phase lag compensator, the phase is going to be negative. So if it is going to be the negative, you will add it on top of this negative phase. So you will drag, you don't make it, the plot rotate clockwise, okay? If you move the plot clockwise, yeah, that's just like you are squeezing the phase margin. You see, you make the alpha smaller and smaller. Okay, and if you have, you can see that if you have too much negative phase, then you're gonna rotate this plot, go this way. You see, if you move it too much, rotate it, the plot clockwise, too much, then the phase margin will become negative. So the system will become unstable. So now you can see that potentially the phase lag compensator actually is harmful for the stability margin. Okay, the phase lead compensator is gonna be helpful for the stability margin. Okay, so I think that is very important for you to realize the difference of the roles of the phase lead compensator and the phase lag compensator. Okay, the roles are different, and one is helpful for the stability margin, phase margin. The other one is harmful for the stability margin. And if you have too much lag phase, and you can even make the system, closed system unstable. Okay. So now, once we understand that, then we're gonna this slide is just okay. Now we need to parameterize the G of S. Okay, we can leave the controller C of S open, completely open. Then you're gonna have numerous parameters to design. Okay, and then eventually you're gonna stop it. You cannot do anything. So we need to parameterize, the controller C of S. In other words, we need to specify a controller to be compensator to be used. Okay, so in this classical control case, we're going to focus on the design a compensator, the controller, in terms of this kind of format. You see, this controller is going to be characterized by 3 parameters: K, which is the controller gain, and the T1 and T2, 2 time constant. Okay, this is the first order, and it's the 2 time constant, numerator, denominator. Okay, and once you understand, okay, I can you're gonna stuck. You don't have nowhere to go. Okay. So if this controller is parameterized, by these 3 parameters, then we need to we can do something. We can proceed. For example, we're gonna find out that it's a frequency response, which is very important for us, right? The frequency response is gonna have this kind of format, and specifically, it will carry a magnitude that that is calculated by this expression, and also I can figure out its a phase, and this phase, it's a phase where it's simply equal to the arctangent omega T1, which is the phase of the numerator, and minus the phase of the denominator, arctangent omega T2, right? See, I can express the magnitude and the phase out in terms of what? 3 parameters. In terms of, actually, the phase is only affected by the T1 and T2. We said many times. The gain K does not affect the phase, right? The gain K does not affect the phase. It will only affect the magnitude, but it will not affect the phase. So this is the case, right? So now you can see that for this specific controller, then what is the phase lead? Yeah, as long as T1 is larger than T2, it will be phase lead. Why? Because if T1 is larger than T2, then this difference is a positive. That's very easy to figure out, right? That's very easy to figure out. And apparently, if T1 is less than T2, then this phase is negative. So you can see we can very easily characterize the phase lead compensator and the phase lag compensator. So next, we're gonna see the example that how we can design a phase lag and how we can design a phase lead. Okay, out to achieve the desired performance. Okay. Now we need to do some calculation. Okay, do some for this compensator. This compensator. Yeah, you can try, to draw is a Bode plot, which is very easy to draw, right? You see, let's do a quick approximation analysis. Okay, let's say for the first case, see, basically you have 3 factors, right? You have 3 factors: 20 log K plus 20 log double bar J omega T1 plus 1 and plus 20 log, actually it's minus 20 log j omega t2 plus 1, right? See, this is the magnitude plot. And for this one, well, we're going to just leave this one aside for a while. And then look at this one. Oh, you know what? This is a standard numerator first order case. We already know how to draw it. Okay, so we identify the T1 over T1 here, which is the separation, the crossover, the corner frequency, right? So because this is a numerator, we know that the plot is going to go from this is the 0 dB, okay? 0 dB. The plot is going to go up to the 1 over T1, the corner frequency, and then what? Then go up. And here is the 20 dB per decade, right? This is what we learned from the Bode plot, okay? Very easy. The approximation can be done, okay? Same thing for the 20 log j omega t2 plus 1, okay? But this time, this is the negative. This is in the denominator, okay? First order, okay? Okay, but when you do the approximation, then there's a good question, okay? It's if it is T1 larger than T2 or T1 less than T2. You know why? Because the two different situations, the corner frequencies order is different. That make a difference. That make a big difference, right? So if we look at the first case, if T1 is larger than T2, which is the phase leader compensator case, then what? Then you're going to have a 1 over T1 is going to be less than 1 over T2. Okay, so now you know that the second corner frequency is going to be here because it's larger than 1 over T1, right? Okay, so you can quickly draw the approximation for the denominator first order is going to go like this, right? You see, downward minus 20 dB per decade. Okay, okay. So now, then what? Then you need to add them together. Okay, okay. So that is very easy to be done. Okay, you already practiced that in a lot of assignments, right? So you're gonna see. Okay, now starting in this range, both of them exhibit a 0 dB. So you still have a 0 dB. In this range, between the first and the second corner frequency, the denominator still show a 0 dB. But the numerator already show a upward, magnitude. So it will stay with this one, okay? It will stay with this one. Okay, after the second corner frequency, yeah, you're going to see both upward and downward. So the offset become flat. Down. This is going to be a phase leader compensator's magnitude, shape. Okay, then don't forget a 20 log k. Yeah, okay. That's just offset either upward or downward, depends on k is larger than 1 or k is less than 1, right? So it is easy to figure out a phase leader compensator shape is here. Okay, then I don't need to explain for the phase lag compensator, right? Because in this case, your second corner frequency is here, okay? It's less than the first corner frequency, right? Okay, so your shape is gonna go this way. Okay, your shape is gonna go this way. Okay, now the question, for both shape, okay, you know what? I can conduct this kind of a calculation. I can find out the peak phase here with the peak frequency m. This is the phi m. This is the phi m. This is the omega m. Okay? And yes, two corner frequencies are the inverse. Yes, yeah, the inverse, yeah. Okay. So, yeah, the calculation, well, this can be calculated from the very simple advanced calculus, okay? Because you have the phase here. You just need to take a d phi omega d omega equal to 0. Take the derivative. You see, this is the very basic, advanced calculus, right? So you're going to be able to find out the omega m and the phi m to be equal to this, okay? Okay? Okay. And not only that, you're going to see the magnitude change is actually equal to this 20 log T1 over T2. You can figure out yourself to calculate this difference. Okay? See, to calculate this difference. You know what? The K doesn't matter here. It doesn't matter what kind of a K value is going to use, because here, this is what we talk about is the difference between the magnitude raise up or roll off, right? Okay. So the K in this process is canceled. So it really doesn't matter regardless of the value of the K. Okay. So this difference, it's always equal to 20 log T1 over T2. Okay. Now here you can see that for the phase lag compensator case, which is this case, you have what? The magnitude is going down. So that is why you're going to have a negative, magnitude change. Okay, negative magnitude change because the T1 is less than T2. This number is less than one number, so the log number is negative. So you're going to see the magnitude is drop. Okay, that's negative. Okay, negative magnitude change. Now, for the phase lead compensator, T1 is larger than T2. So this magnitude change is positive. It's a roll off, raised up, right? It's a positive. Okay, so it doesn't matter. You can always use this formula. Okay, it will automatically tell you what is going to be the situation. Okay. On the other hand, you can see that if T1 is less than T2, then numerator here is what? Is negative number. So that is why you have a negative phase. And when T1 is larger than T2, this number is going to be larger than 1. So that's why you have the phase is going to be positive. Okay? Right? Okay? So this is very simple to be figured out. Okay. But I want to tell you is that we need to recall, I've just said that the phase lead compensator actually is helpful for the stability margin solely because what? Because it can provide a positive phase, right? And the phase lag compensator is harmful for the stability margin because it provides negative phase. So from this two figures now, you can figure out if you want to use the phase lead compensator, you are actually interested in using the information around the peak frequency, peak phase, right? Because you want to take the biggest advantage of the phase lead compensator, because you need its positive phase. Apparently, you want to use its positive phase, you got to dig out the potential as much as you can. And that is exactly the peak phase range. So you can actually pretty much sure that you want to design a phase lead compensator. The game is going to be played around this area. We want to take the advantage of this peak phase area. Okay? You're going to see that later. Okay? You're going to see that, when we present the example. Okay? On the other hand, okay, for the phase lag, compensator, can you tell me, should I be interested in this range? Someone tell me? If you can answer it correctly, we're going to wrap up the class. If you don't answer or answer it incorrectly, we're going to continue. Okay? Someone, please. You don't want to leave? Fine. Okay? Come on, someone, please. Zia, why it is not right? Why it is not right? You see here, this is a peak phase. It's negative. You add this much of a negative phase to the system, how do you expect that the system stability margin is going to be, right? This could be very, very harmful. Not only harmful, but you are hurt the system the biggest time, right? You see, you're using the maximum negative phase, okay, to the system. So you can imagine, definitely, if you want to use a phase lag compensator, this range is what is you trying to avoid, okay? You're trying to avoid, okay? And I can tell you that for a phase lag compensator, the interested frequency range is here, okay? It's actually a high frequency range, okay? Because in this range, you see the phase lag's impact is what? It's diminished, okay? The negative phase provided by the compensator, it's almost diminished, okay? So that's what I want. I want the harm, it can be contained, okay, as much as I can. So exactly, I'm interested in this area, okay? Why not the low frequency area? You're going to say that in the low frequency area, the negative phase is also small. Why we don't want to touch this part? Because someone, well, this might be, this is not that straightforward. Well, it's kind of, tricky. Okay. So can someone give me an answer if you can? Well, this is not a judgment. This is going to be the last question. Okay. It doesn't matter you answer it correct or not correct. I will let you go. Okay. But I want you to answer that. Why I don't want to, I'm not targeting on this area to do the control design. What will, if I touch this part, what will be changing? Can you have this kind of a sense? Someone? Last question. Okay. See, I don't want this range. I'm not going to play this range. Okay. I'm going to play this range. I've already tell you the answer, right? So, but why I don't want to play this range, the low frequency range? Someone? Not really. You see, like what I said, actually you see in this part, you can see the phase lag is also small. So if you play in this range, it will not harm the stability, at least it should be the same, level as the high frequency range, right? So if I don't care about the high frequency range, I should not care about the low frequency range. So this must be some other reasons, okay? This means that it must be some other reasons. What is that reason? You see, in the low frequency range, did you notice that the magnitude of the phase lag is what? It's come down, right? It comes down. So what does this mean is that the highest magnitude happens in the low frequency range. Okay, now what does that mean for the closed system in performance? You see, for the tracking. I don't want to touch this part, is that I want the low frequency range, the magnitude stay high, okay? Because if I play in this range, there's a good chance for me to drag this magnitude down. If I drag that magnitude down, then I'm gonna, affect my tracking performance. You see what I mean? So that is why we would rather to leave the low frequency range as much as it can be, okay? As much as it can be, okay? And we do not want to touch it, okay? Because it's already high, let it go, okay? Leave it high, because it will help the tracking. So we do not play in the low frequency range. If we play it, we're gonna have a good chance to drag this magnitude down, okay? If we down, it will hurt my tracking performance. So this range I want to avoid. This range I want to avoid. All the games can be played only in this high frequency range. We're going to see that in the next class, in the examples. Okay. So if you can, read the example first. So next on Wednesday, when I come back to talk about it, it will be easier. Okay. Any questions? And now this classes will stop here. So I will take your questions. Okay. If you want to leave, you can go ahead. Okay. Any question? No more question? Okay. Thank you, Tara. Thanks, Zia. Okay. Yep. Okay. All right. Okay. Yep. See you on Wednesday, Iman. Remy, thank you. Okay. All right. No more questions. So I will close the classroom. Okay. All right.